Okay, so thank you all for coming. I will. So this is the last talk, which I know what I'm going to talk about, of course. So let me start by recalling what I did last time. At least this I know, kind of. So we had this groupoid. And we gave on this a smooth structure. And so we can talk about, so this is a smooth manifold. In fact, it's a Lie groupoid. And so we can talk about smooth functions on this thing. And we discussed this formula, so we can take this integral. And we also equipped this with an action. We had an action of r plus star on this space. Dilation action, so lambda gives me a map from a diffeomorphism. And we discussed this theorem of Dabo and Skondalis. Which is that if I start with this, here I should. So if I start with some smooth function with values on half densities, and I consider this integral, so for all k in C with real of k negative, this gives me a pseudo differential. So this integral is well defined, gives me a distribution on this groupoid. And if I call this, so we discussed this and this integral, and if you restrict this to m cross, so m cross m cross 1, then this is a classical pseudo differential operator of order k. And all, and this and all pseudo differential classical pseudo differential operators can be written this way. So if you remember, we had two problems here, which I said I will discuss. So the first problem was convergence of the integral, and the second problem was this condition. And convergence of the integral, we didn't have any issues, because so convergence of the integral comes from this fact that if g is a C infinity function here, then this function so there's two, but I'll do one of them. So this admits a smooth extension to R plus. Also, you can do the same thing with the other way around. So to explain what's going on here, this dilation action, it was only defined for R plus star. And the point is that even though I cannot define alpha 0 as an operator on my space, I can kind of define it as a distribution. So alpha 0 of f, this is well defined as the limit, so the value of this at 0 after you extend it uniquely, and this would be in C minus infinity of Tn. And this thing would be just Dirac, the integral of f multiplied by a Dirac over the space of objects, so Tn. Yeah. And so this explains why this integral converges, because obviously this is a continuous function, the only problem you have is at 0. And so if k satisfies this condition, then this becomes a continuous function on the interval, and so you don't have any, or integrable function on the interval, and so you don't have any problems. Now I'll discuss what you do to get rid of this condition. And so to get rid of this condition, we will have to put some restrictions on the function. So I'll explain where these restrictions come from. And at the same time, the type of restrictions that we will put are precisely the technique that we will use to prove that the principal symbol, both the classical principal symbol in this setting, but also the principal symbols that we defined using representation theory on Hormander's condition, are well defined. It's the same idea. So, is it good for everyone? This is what I did last time. So I don't need all of this. So let me recall what I said last time. So if G is a Lie groupoid, then we have a map. I defined two maps. So I defined one map from the smooth functions, there is no densities, on the space of objects to distributions, which is just Dirac on the space on the units. And I defined another map, which is sections of G, 0, the Lie algebroid, to also this, which are basically derivatives of those things. So they are differential of Dirac. Again, the distributions here are supported on the space of objects. Now we will apply this here for this groupoid. So in this case, A of G, A of Tm, this is just Tm as a vector bundle on M cross R plus, because this is a groupoid, the space of objects here is M cross R plus. I mean, yes, it's a pullback. Yes. So it's a pullback of the tangent bundle on this product space. Now, here, I will not be interested in all sections. I will just be interested in the sections which don't depend on the time. So these are just vector fields. This map gives me sections on M cross R plus. I'll just be interested in these sections. And here I also have C infinity functions on M cross R plus. I'll not be interested in all C infinity functions. I will also just be interested in C functions on M. I can do much better if I put them this way. Then it follows the same order as it, which looks better. Anyway, so I have a map which takes C infinity functions, gives me distributions. I have a map which takes vector fields and gives me also distributions. Now I remember that any differential operator can be written as a polynomial with coefficients in C-infinity functions of vector fields. And thus, I can put these two together, since this is an algebra, and get something for all differential operators. So if D is a differential operator, then I can define, and I write it D as a polynomial in the vector fields, on some vector fields, x1 till xn. Then I can define a map. So to be very precise, I will call this map theta 0, and I will call this map theta 1. And so,
yes, last time we talked about C minus infinity, in particular, subalgebra C minus infinity.
yes.
So,
So I recall what is.
yeah, no, just the image is in this subalgebra, but they are also distributions. So
Yes. So it's also.
I mean, I listened online, and I think Claude was always asking if it was RF, but he's
Yes.
so I will replace Claude.
What is the question?
Exactly this.
It's RS. Yes. Yeah. So I forgot. Here it's RS. It's always RS. I don't care about all the others. It's only RS. Which maybe before I give the definition for the differential operators, I recall what these things do. So the convolution with them. This will explain what's going on. The reason for the index is that these things are differential operators of order 0. These things are differential operators of order 1. And so once I define them for all differential operators. So let me recall. So theta 1 of, say, a vector field. And I take a function here. So I'm taking a function on C infinity C of this space. These half densities. And so this function, if I want to understand it, I just need to understand what happens here by density. I can also describe what happens on the right-hand side. But, so it's x, y, and t. And so it will be x multiplied by t of f at x, y, and t. So this means that x acts on the x variable, so on the first copy of m. And this is left convolution. Right convolution would be the same thing, but you would act on the right, on the y variable, and probably with a sign, I think. Okay? Now, and at 0 you would act, so theta 1 of x star f at v, x, and 0 would be x of x applied to f at v, x, and 0. And now I have to explain what this means. So x is a vector field. It's this. d over ds at s equal to 0, f of v plus x plus s, x of x, x and 0. So essentially your vector field x, you evaluate it at the point x, and then you see it as a constant vector field on the fiber, and then you differentiate along this constant vector field. So it's this. And you verify immediately from the way this, the smooth structure on this was defined that this is a smooth function. So this is what defined. But this was also true for any Lego point. Okay? Now I can do, I have to erase this. Now I can discuss differential operators. So now I have D, differential operator of order k in M. So D, I can write it as a polynomial in some vector fields, where are some vector fields here. And so the idea is that I'll do the exact same thing. So I want to define theta k of D. So I will write it this way. I will explain what's going on. So what this means is as follows. So what's P tilde? P tilde means I make my polynomial homogeneous by adding t's. So let me explain. So say my polynomial was something like this. P of x1, x2. Say it was some differential operator which uses two vector fields, and it was something like this. Say this is my differential operator. I have some two vector fields on a manifold, and I do this. Okay. Now, if I apply theta in a very stupid way, where I just apply theta on each factor, so I will get, so I say I take theta 1 of x1 square, theta 1 of x2 plus theta 1 of x2. Remember that I'm allowed to take square, I'm allowed to multiply, because this thing is an algebra. So I can do this. Okay? So say I do this. Then I can ask the obvious question, well, this thing obviously depends on how I wrote my differential operator as a polynomial. And so say I write the same differential operator as another polynomial. Do I get the same operator on the group weight? And the answer is no. Because, so if you look, all you have to do by density of m cross m cross r plus star in Tm, all you have to think about is it well defined just on this part? Okay? And the problem here is that theta 1 introduces a t factor. And so this thing, if you let it act as it's written, if you let it act on a function, it will be as if you multiply with t power 3, because each one of here will introduce one factor of t. And so it will be x1x square x2x. This means that x1 and x2 act on the x variable. Plus, but here you'll only get one t. And then you add f of x, y, and t. And so this is not your original differential operator. This is not the differential operator. So this is different from what D is. So the idea is that you add powers of t so that this becomes homogeneous, and this is well defined because at t non-zero you get your differential operator. So what this means is that theta, so in this case you will define theta 3, because this is a differential operator of order 3, you will define theta 3 of D as theta 1. So the correct definition would be this. Plus, and you multiply with t square theta 1 of x. Now, this one, just like this one, a priori depends on the way my differential operator is written as a polynomial in the vector fields. But the advantage of this one is that I can prove that it doesn't depend on the way my differential operator is written on the vector fields, because once I let it, so this one, once I let it act on functions, I will have t squared here, and so here I will have t3, and so I can get the t3 factor out, and so it's just t3 dx f of x and 1. It's my differential operator acting on f on the x variable multiplied by t power 3. So it doesn't depend on how I wrote my polynomial, my differential operator as a polynomial in the vector fields.
As far as you choose the order.
As far as you choose the order. So that's why my theta started with the order.
But the way you explain it, you do it because it's convenient.
I mean, it's so, okay. It's essentially the same thing you do when you define the principal symbol, in the sense, okay, so here there is no t, but here there is t. And so look at this distribution, and then look at what happens at t equal to 0. And so everything which has a t will vanish. And so the things which don't have t are precisely the things of the highest order. So it's basically a trick, which goes back to Alan Cohn's work, to force your differential operator to act. So you have this Tm to act here by t power the order of your differential operator on the first variable, and at 0 you act only by the principal symbol. So it gives you a canonical way to make a deformation between your differential operator and its principal symbol. I do it because it's convenient, but it also works. So and is this clear? So this map gives me a well-defined. So now I can erase this, all of this. And so I get a map. So putting all of this together, I get a map from theta k, from differential operators of order k, and a manifold to these things. Which is theta k of f, of some differential operator acting on f. On the non-zero part, it's just t power the k, the differential operator acting on the first variable. And at the 0 part, so at the 0 part, because powers of t will appear at everything except the classical principal symbol, so it's the same as the classical principal symbol, but it's Fourier inverse of this. So this is basically, so it's, how do I, it's a classic, so it's this thing. I will write it this way. Sigma of d f inverse applied to f on v x and 0. So what is this? So if my differential operator is locally this sum, so locally if my differential operator is this sum, then this thing is the constant coefficient differential operator, which is you just kill. So first you kill all of the lower order sums, which is the same thing you do in the classical principal symbol, and you take f alpha of x, you freeze coefficients, and in the classical principal symbol you would replace these things with ixi. Here you don't, you just see it as a constant coefficient differential operator. So it's the Fourier transform of your principal symbol. and you view this as a differential operator. dv, yes. And you view this as a differential operator, but instead of acting on the manifold, now it acts on the tangent space. And so this thing means that it acts on f on the v variable. It's the same thing as just writing my differential operator as a polynomial and applying each vector field. So this is the principal symbol. It contains the exact same information contained in the principal symbol once I take the Fourier transform. So now I'm almost, I can almost finish because I have C infinity function with compact support here. So this we were able to define because this thing has a smooth structure. So it's a Lego point. Now I will define if K is in N. Things which vanish at 0 to the order k, in some sense. And these are, it's very simple, it's just theta k of do k of n star c infinity c of tn. So this thing means, I can also do it the other way around. So it's all of the things which I can write as some finite sums of theta k of some differential operators of order k with some functions which are in C infinity. So these are the things which vanish to order k. So for example, what is C infinity C1 of Tm? This would be the functions here. So you can prove this in a rather easy way. So this is the C infinity functions with compact support here, such that for every x in M, the integral of f of v x and 0, so you integrate over v, so the integral on the tangent space, so at 0 you integrate, this is 0. So this is things which vanish to the order 1 in the sense that their integral vanishes. This is what I mean by vanishing to the order 1. Higher k means that this integral vanishes to higher order. Basically that when you take the Fourier transform of this at 0, it vanishes to higher order. Because at the Fourier transform, this is the same as saying that this vanishes, the Fourier transform vanishes at the origin. If I take the Fourier transform of f at 0, this condition just says that the Fourier transform vanishes. But the advantage of this approach is that I don't talk about the Fourier transform. Why this thing is useful is that everything is algebraic. I do operator algebras. I really like algebra when it's done into analysis. So the advantage of this approach is that everything becomes algebraic. I used crucially the fact that every differential operator is written as a polynomial in the vector fields. I didn't have to think about what is the Fourier transform. I didn't have to think what is this thing to define my objects. They just happen to be the classical objects in this case. And so everything, once I replace my space here with another space more adapted to the problem for Hol-Mandas vector fields, everything will work exactly the same. So this is the advantage of this approach. I don't have to think. And so now I can state the theorem of the Bohr-Skandalys. And Scandalise. Now, if k is any complex number, and f would have to vanish at, so k is not necessarily a natural number, but you would need to vanish at least L, where L is bigger than the real part of k. L is something in N. So here I defined k. By analogy, I would define C infinity C0 to be just C infinity C of Tn. By convention, I would do this. And so if the real part is negative, so if the real part is negative, I could just take any C infinity function. But if, for example, k is 0, then I would need to take a function which vanishes at least to the order 1, and so on. And then the integral, then this. So it's so L is, if you want, L is the maximum of the higher integer part plus 1. The smallest integer which satisfies that L is bigger than the real part of k, which I have no formula for this. What? And then you take max with 0 because you don't want a minimum with, I don't know. I don't care. Then this, so the integral converges and defines an operator here, Rs, converges as a distribution, and gives me, and when I restrict it to 1, it gives me a pseudo-differential operator, a classical pseudo-differential operator. And all of them can come this way. So I take u to be this integral, and now if I restrict it to m plus 1, then this is a classical pseudo-differential operator of order k, and every classical pseudo-differential operator of order k can be written this way. You could also say more, that if you restrict to Tm cross 0, then this is not the classical principal symbol, but it essentially contains the information you would need to define the classical principal symbol. I will not go into more details, but here you take the integral from 0 to 1. You restrict at 0, and you change the integral from 0 to 1 to the integral from 0 to infinity, and that would be the principal symbol. You can make it canonical by saying that the principal symbol of your u restricted at 1 would be the limit as lambda goes to infinity of alpha lambda of the restriction at 0. I mean, it looks an awful formula, but so here you would get something. The principal symbol of this, the principal symbol of u restricted to this is this thing. But instead of integrating to 1, you integrate to plus infinity, and you would restrict to Tm equals 0. And that would be the classical principal symbol of this pseudo-differential operator. Yeah, so this seen as a distribution on Tm, if you want it to be the classical principal symbol, you would have to take the Fourier transform of this distribution, and then that would be the classical principal symbol in the usual sense. Which is not defined at 0. So this is a distribution not on all functions, but on functions which vanish, whose Fourier transform vanishes at 0 fast enough. These are technical details which are not very relevant at this point. So all of this to say that this approach gives me a way to define the classical principal symbol connected with classical pseudo-differential operators, define classical pseudo-differential operators, all thanks to this piece. Which happens to be a Lie So if I want to do all of this, but in the context of vector field satisfying Horman's condition, really the main step would be to find the correct generalization of this space. And then once I do this, I basically follow, I have a recipe to do all of these things, pseudo-differential calculus, principal symbol, and so on. So I just follow it. And so now I'll describe this space, which will be much more geometric. So. So my context, I have M in a smooth, now any smooth manifold, and I have some vector fields which I fixed, which satisfy Horman's condition. And I suppose that N is some natural number which is for all x in M up to n commutators are needed. Iterated commutators. N is the depth, not the number of commutators I use. So at most I use commutators of depth n are needed to span Xn. This is not a restrictive condition because locally it's always well defined. I could do the construction and n would be a locally constant function, not continuous. But I could do the construction without supposing that this is finite, just makes the construction only slightly more complicated. Okay? And now I have G, the free nilpotent the algebra of depth n, and with one generator, with a generator, with one generator, with generators, and it has n generators corresponding to these vector fields. So this is G. And since it's the free nilpotent algebra, it is graded. It's graded by the number of commutators you use. So G1, for example, would be R x1 tilde plus R xn tilde. G2 would be generated by direct sum I less than j r xi tilde, xj tilde, and so on. This is G2 and others. And because it's graded, I have graded dilations. So for every lambda in R plus star, I have graded dilations. I'm recalling all of the things we did from before. And I have G. Do I need this? Yeah, I probably do. G is a free, it's a simply connected Lie group integrating the Lie algebra. Now, and I also had this map from the Lie algebra to vector fields. So this is a linear map which sends, I should make use of space. So sends xi to xi and commutators to commutators and etc. And we already discussed that this is not a Lie algebra homeomorphism. And so I had this thing, which goes from G to TXM, which is just this map composed with evaluation at X. And this map is surjective. I'm just recalling the construction of the tangent spaces, which I did either last time or the time before. I forgot. And then, okay. Yeah, and then to define the tangent spaces on Sub-Riemannian geometry, what we did is we took the kernel of these maps. So we looked at the kernel of these maps, and then we multiplied with dilations. And we took limits as t goes to 0 and x sequence xn goes to x and tn goes to 0. Okay? Now I will do this, but in a much more conceptual way. So just to see what I'm trying to achieve. This groupoid, its space of objects is M cross R plus. Okay? Now, this groupoid, I think of it as something which belongs to Riemannian geometry. And so the space of objects is basically the space of tangent spaces. So one point for every tangent space. Now, I want to define the analog of this in Sub-Riemannian geometry. And as we discussed, in Sub-Riemannian geometry, every point doesn't have one tangent space. And so actually, all I'm doing here is defining the space of objects of my groupoid. Then once I can do this, I can construct the actual groupoid. Okay? So now I have a map, I have an inclusion map from M cross. So at the non-zero part, so we'll construct a groupoid, which will be this, union something at the non-zero, at the zero part. So at least on the non-zero part, I know what I'm doing. It's just at the zero part, which I'm trying to change it. So I will take this inclusion. It's an inclusion because of, so this is a Grassmann, because I will basically put the identity map in it. So it takes x and t and gives me the alpha t of alpha 1 over t of kernel of this map x and t. So this is obviously a topological embedding because I put the identity. Now I can define my space of objects. It's just a closure of this thing. In the image. This space is locally compact, and so this space is also locally compact. If M happens to be compact, then at least at 0 you just add the compact things. Okay, and as I said, this is equal to M cross R plus star union so this is a space of all tangent spaces. So this is G x0 is a space of all subspaces such that you can find a sequence xn which goes to x, tn which goes to 0, such that alpha 1 over tn of kernel of this goes to H. Okay, so this thing we already discussed properties of the things here. And the main properties we discussed are, so the first property is that for all H here, H is a Lie subalgebra. Of G. We already discussed that this thing is not a Lie algebra homeomorphism, so the kernels are not Lie subalgebras, but at the limit they become Lie subalgebras. And the second property we discussed is that for every G in G is a group which integrates my Lie algebra, G H G minus 1 is again for, and H here, this is again, okay? If you want the proof of this fact, it's actually quite easy. Given what I reached so far, I can explain it very quickly. The idea is extremely simple. On this space, you define some vector field. This is some formula which you can use to define a vector field on this smooth manifold. And you show that this vector field on this part, it's tangent. So on the image of this, it's tangent to the smooth manifold. So its flow preserves this part. And since the flow of a vector field preserves this part, it preserves its image. So the image is also invariant on the other flow.
What you say is for every element of the Riemann of G.
Yes. For every element in the group, or the Lie algebra, you can define a vector field here, which at t equal to 0 becomes just conjugation here by G. And at t non-zero, it's tangent to this. And so the flow, because it's tangent to the smooth manifold, its flow preserves the submanifold. And so its flow also preserves the closure. And so you get this. So the proof is not that difficult. And the formula for the vector field is quite simple. Once you write the formula for the tangent space of the Grassmannian, you can just guess it, more or less. Now, I talked about constructions of Lie groupoids, and I said that the most important, this was last time, the most important construction for me is taking a quotient of a group by a subgroup, by a family of subgroups which are not normal, but they are closed under conjugation. So now I have a family of Lie subalgebras, but of course I can integrate them and they become subgroups. So I have a family of subgroups which are not normal, but closed under conjugation. So we can define the quotient of this group. So I write it this by this set. So this is a set of all GH, left or right, it doesn't matter, as I explained last time. G in G and H now is a group which integrates. I use capital because it's a group which integrates here. So this is a group which integrates the Lie subalgebra here. I will abuse notation, just write this. And we discussed that, and we said that this is a groupoid. So we said that this is a groupoid. And if you remember, its space of objects was this thing, with the set of subgroups themselves. Now I notice that here I have this space of objects. So I now can define my groupoid, which would be, I put all of these things together. At 0. And now this is a groupoid, its space of objects is precisely this. And as a groupoid, the algebraic structure is just disjoint union of these groupoids. And the pair groupoid. So here I didn't change anything from what Kohn is doing. It's only here which I change. And the motivation is exactly the same as what Kohn had, it's just that my situation is slightly more complicated in the sense that in what Kohn had, or in classical pseudo-differential operators, you want your principal symbol to live on Tm. Here, if I say I believe, before I start, let's say I believe the Helfer-Noriga conjecture, and they tell me that their representations come from this tau x, the set tau x. And we understood that this set tau x are the representations which are weakly contained in the representation of G on L2 of G over H, all of the homogeneous spaces. And so I need to find a way to put all of these representations together at 0. Okay? So the motivation behind this construction is basically taking what Helfer and Noriga suggested and try to find an algebraic construction or an algebraic groupoid construction behind it. If these groups were normal, everything would be much simpler, because here I would just put the quotient of the group with the subgroup. The groups are not normal, and there's multiple of them, and so I put all of them together, and so I use this construction which I discussed from before. So this is a groupoid. So this is a groupoid. But of course, I don't just want, I need much more than the algebraic structure. The algebraic structure is very nice when I want to do convolution later on, but I still want to discuss the smooth structure. I need to put on this a topology. Okay, so I can now explain what the topology comes from, and I really shouldn't erase too much. What can I erase? So I will rewrite this here, and then I will erase the rest. Yeah, so this is important. So this space G0 was defined as the closure of some space in Riemannian G cross M cross R plus. So G0 has a topology. My problem is defining the topology on G. G0 is closed set inside a smooth manifold, so it's fine. Like this I can erase it. So I will define a map. Where does it come from? It comes from the article of Androuladakis and Skondalis, because this is a special case of some blow-up construction of some singular foliation. Since I'm not doing at all of this, the map might look like it's mysterious, but it's not that mysterious. In Conn's construction, you have y, x, and t. And so what Con does is that, if you look at it using sequences, what Con does is that a sequence here converges to v, x, and 0. Here it's an element in Tm cross 0. If there is three conditions, xn and yn goes to x, Tn goes to 0. These are the usual conditions, and the last condition, which is the one which interests me, is yn minus xn over Tn goes to 0, to v. Where here you are doing the computation, so yn and xn get really close to each other, so I can look at the difference between them. It becomes a tangent vector. I divide this tangent vector by Tn, and I ask that this converges to v. Okay? And so the construction that I will do is it basically replaces yn minus xn with the flow of the vector fields which I started with x1 till xn. That's basically it. So the map, and just to be clear, what I will do is that I will construct a map which is surjective on this space, and I will give this topology the quotient topology. So the map is, I start with the Lie algebra cross this thing. And I will define a map from this to G. Okay? Now, what is this map? So, there is two types of elements here. Elements which come from non-zero part and elements which come from the zero part. And so, if my element doesn't come from the zero part, what do? I flip this formula. So if this formula you write it as y minus x over t, then you can write it as y equal tv plus x. So this is the flow of x starting from x in the direction of v. And so this becomes, so I send it to, so I will send it to a point here in m cross r plus star. So the first, the second, and the last, it's x. Here what I will do is that I will take E. I need slightly more space if I want it to be readable. So I will do x and t. I will take the flow of this. So this is the flow. Alpha is the dilation, which is the same as multiplying by t in this formula. So G is an element in the Lie algebra, so I can take its dilation. So that remains an element in the Lie algebra. Then once I take this map, it's now a vector field on my manifold. I take its flow at time 1, starting from x. And so it just replaces this formula. And that's my y. Okay? What I do if it's an element at 0, So if it's an element at 0, that means it's a subgroup or a sub-Lie algebra. Lie algebra. I identify the Lie algebra with this subgroup. So what happens if it's an element of this form? Well, this is very easy because elements here are cosets, so I don't have to think about it. I just take the product. So I just take G, H, and X and Z. I just multiply. It's a group, and I have an element. Exponential G, yes. Because G is an element in the Lie algebra, I view it as an element in the group, and then I multiply. Yes, thank you. Okay, so now, is this surjective? Is this surjective? The fact that, so I will remark something, it's not very important. It's not technically well defined everywhere because it's the flow of some vector field which might not be defined everywhere. It is technically well defined when G is small enough or when T is small enough, because this thing would be small enough, and so it's a flow of a vector field which has some Cn norm small enough. Okay? So it's technically defined in a neighborhood of at t equal to 0. Okay, but let's ignore the issue of is it well defined. It's well defined on an open set, good enough. Is it surjective? Obviously, at 0 it is surjective. There's obviously no problem. At t equal 1, at t non-zero, it's surjective if these 2 points are close enough to the diagonal. Away from the diagonal, it's not surjective, because it's not necessarily true that if I have 2 points on the manifold far away from each other, I can go from one to the other using something like this. I can certainly do it by concatenating flows, but not necessarily one flow. So it's surjective near the diagonal. So the image contains an open, I didn't define the topology, but okay, so if I want to view it surjective, I can cheat in a very stupid way, and I can just do this. I will describe the topology in another way in a moment. So this union, disjoint union, M cross R plus star to G. And the map here, it's the map which I described. Here it's just the inclusion. Now this is obviously surjective. So this is surjective. I give it the quotient topology, and I give this the quotient topology. Okay. I will remark something. I don't really, I won't really use it because it's, I will go to my index theorem in 20 minutes or so. But when I'm doing classical pseudo-differential operators, I needed more than a topology. I needed C-infinity functions. Okay? And so I also need to talk about C-infinity functions. So how do I define C-infinity functions on this? I define them the exact same way. How do you define the quotient topology? A function from this to R is continuous if its pullback is continuous. That's literally the definition of the quotient topology. And so I'll say a function from this to R is smooth if its pullback by this map is also smooth. And I can define smooth on G0. So here, this is a smooth manifold, so there's no problem. Here I can define what it means to be smooth because G0 was a closed set inside a smooth manifold. So it also comes with its own notion of smooth. And so I can talk about smooth functions. For convenience, I will just ignore this. But that's how I will also talk about smooth functions. Now, let me talk about properties of this topology. It might not look like it, but this map is open. And this topology is, so G is locally compact. Second countable, Hausdorff. Yes?
The problem of like choosing an open domain so that it's well defined, isn't it also like if you take a too big domain, you could also have an Hausdorff topology if it's not in the injectivity radius of the exponential? It's just for the well-definedness, the well-defined.
You don't care about what the domain looks like. Here you don't care which domain, as long as the flow is well defined, you're good.
Even if it goes back to starting point?
Even if you loop around, it's fine. Any open set here, as long as your flow is well defined, you're good. You can take the quotient topology. Okay. The reason is extremely simple. The whole problem in defining this topology is what happens at t equal to 0. And at t equal to 0, you know that there is an open set which works. So you don't care. Any open set, as long as you restrict to an open set on which this flow is well defined, this will be the quotient topology of this. And the topology will not depend on the open set. And it's locally compact second countable Hausdorff. Hausdorff is not trivial. Okay, but I don't have time to give you the proof of this fact. I have time to give you a description, a nicer description of the topology of this thing.
You can embed it in something.
You can also embed it inside. So just this is by classical theorems in topology. This implies it's metrizable, but you can do much better. You can actually embed it inside a Euclidean space as a closed set, and and you can and even the smooth manifolds, the smooth functions that I just described would be the smooth functions which extend to the Euclidean space. So you have some sort of Whitney embedding for this. But of course, the embedding is not canonical. It exists. So let me describe the topology. I will describe the only interesting part of the topology, which is how I glue this with what happens at 0. Okay? So
So what you're saying about the topological properties of G, are they general to this globe of singular foliations construction? Or is it
are the two properties true for blow-ups of general singular foliations, which I define in my article? Hausdorff, certainly not. Locally compact, yes, if you define it without the Hausdorff assumption. Second countable, yes. Smooth functions, yes, as long as you live with the fact that your functions are not. Yes, there is a problem of Hausdorff.
So there's something also very specific to this singular foliation.
Yes. And I don't know how to. I don't know how to characterize the singular foliations for which the blow-up construction after I do my blow-up construction of the groupoid that under Ladek is unsconded is defined, gives you something which is Hausdorff. It's not so clear to me what should be the correct conditions. Okay. But in this case, it's true. So, really, the only question, the most interesting question is how does a sequence, how does some sequence here converges to a coset here? So, X and Z. Okay? I want to understand, I like to understand topologies in terms of sequences. So how does this happen? So it's like in Con's case. So I'm not crazy. I mean, maybe, but not here. So Tn has to go to 0, and Xn and Yn has to go to X. So at this part, it's not crazy. The rest is that, so it's two conditions. So I could find some sequence Gn in the Lie algebra, such that, yeah, I forgot. Sorry. And so the second condition is that the coset at least H is determined by the Xn and Tn. So what's this? H is the Lie algebra of the subgroup. So this is the same as, so those two things is the same as saying that Xn and Tn goes to H, X and 0 in G0. Okay? So this is the same as saying that the source map is continuous. I now, at the end, need to determine the coset. This condition, I didn't have it in the case of Con, because there was only one tangent space. But now I need it because there are multiple tangent spaces. And then the last condition is that I can solve the flow problem, which appeared in Con's case. So in Con's case, Yn minus Xn is unique. So I can talk about Yn minus Xn. In my case, my vector fields, maybe there are many more than the manifold. And so I potentially have multiple ways to go from X to Y using my vector fields. And so the third condition is that I can find some solution. So I can find some Gn in the Lie algebra such that I solve the flow problem. So Yn becomes the exponential, the flow of these vector fields, Tn of Gn at X, n. So this is the same as taking Yn minus Xn over Tn. If the vector fields were constant coefficient vector fields in the coordinates. But written in a different way. But it's the same equation as the one from before. So, but then the difference from the case of Con is that in Con he has a unique Gn which solves the flow. Here, because my Lie algebra has a higher dimension, I can solve the flow. Hormander's condition tells me that the map, this map is a surjective, so it's a submersion near the diagonal. So I can solve it, that's always true. But it's not unique. And so the third condition, I can solve it, and this converges to any element here, to an element in GH. Okay. Or you can just force it to be G. In fact, what you can show is that if you can do this with one element in the coset, then for any other element in the coset, you can find another sequence which solves the problem and will converge to this new element. So if you can do it with one, you can do it with all of them. So this is the topology. Now, I will erase here.
And it's the same as saying that J and H converges to GH in the Riemann.
Gn multiplied by this? What was the question?
G and H converges in the natural topology to GH.
Yes, if you define not the Grassmannian, but the Grassmannian of all of the cosets. Yes, the affine Grassmannian. Then it would be also equivalent to asking that just Gn multiplied with these things converge to GH. Yes, which is probably cleaner. But you would have to define the affine Grassmannian. So now I can define our pseudo-differential operators. So in the case of Debord and Skondalis, it was a theorem because the classical pseudo-differential operators already exist. Okay? But here it will become a definition. Okay? So the first thing is that I need the dilations, so that if lambda is in R plus star, then I have a map alpha lambda, which is an automorphism of this, which is as follows. So alpha lambda of y, x, and t is, so here it is the same thing. It's exactly the same as in Con's case, and at 0, you can write it in two different ways, they are the same. You can either write it as alpha lambda of the coset itself, or because alpha lambda is a group homomorphism, you can just write it as alpha lambda of G, alpha lambda of H. And it's very easy to see that alpha lambda of H also has to be in the tangent cone, because if your H can be obtained as this kernel, then you just dilate the Tn, and that would also prove that the dilation of H is also a tangent cone. If H is a tangent cone in sub-Riemannian geometry, all its dilations are also tangent cones. And so this thing is, again, and this is an automorphism. The fact that it's a groupoid automorphism is easy because alpha lambda were group automorphisms. That's not a problem. You can also very easily show that it's C infinity continuous. C infinity because you can just lift it to the before you take the quotient maps. Okay, and now we can define our pseudo-differential operators. So again, I run into the same problem. If k was complex with real part negative, I don't need any conditions on my functions. But if k was complex with real part positive, then I need conditions. So I will start with the negative part. So if k is in C, and its real part is negative, and f is in C infinity, C of this space. So I said that I can talk about C infinity functions. I can also define this bundle of densities. I will not really mention how, but it's related. It's related to the fact that this groupoid Gx, its fibers is a smooth manifold. because when we defined this bundle of half densities for Lie groupoids, we used the tangent space of this. And so it happens that for this groupoid, the fibers are smooth manifold. If gamma comes from a non-zero element, then this thing is just M, so there's no issue. And if gamma comes from, so if gamma is H, X, and 0, then these are all of the cosets on H, so this thing is just G over H. And it happens that for nilpotent Lie groups, so here I use crucially the fact that the group is nilpotent, all subgroups, connected subgroups are automatically closed. And so this thing is smooth manifold. Okay. It's trivial, but it does play a role here. Okay. I remark that here it's trivial, but for singular foliations it's true and not trivial. So it happens that for singular foliations, so back to your question from before. So for singular foliations, it's also true that these types of quotients are smooth manifolds, but it's now much less trivial. Okay. So now if I have a smooth function, now I can take the integral from 0 to 1 alpha lambda of f d lambda over lambda 1 plus k, and this will give me a distribution R and S of G. Now, here is where things get a little bit interesting. This is not a smooth manifold. So I could think for hours what it means to define distributions on something which is not a smooth manifold, and maybe I will succeed, maybe I won't. It doesn't matter, because that's not how I will use distributions. And instead, what I will use, the way I use them is that they are multipliers of the algebra of C-infinity functions. They are things which multiply left and right. And so this thing is well defined once this thing is well defined. So I don't even have to think what it means to be a distribution. It's automatically well defined once I define this algebra. And so I have this thing, and I can restrict them to M cross M plus 1. And so these things will be maps from C-infinity. So there will be maps from C-infinity of M with half densities to C-infinity of M with half densities. And these are the pseudo-differential operators, our pseudo-differential operators. What? Of negative order.
You gave me doubts. Can you re-explain why C infinity of G omega 1/2 is well defined if G is not a smooth manifold?
So I said, so the way I defined it, so this is what I said very quickly. The way I defined the topology on G was a quotient of something here. And this thing had a meaning for what it means to be smooth. And so if G is a function here, I pull it back, and I say it's smooth. If it's pulled back, it's smooth. So. Now, the advantage of this is that I also have the principal symbol. If I restrict U to M to G to the part on 0, so then this is the principal symbol. So this is the principal symbol. So the integral. So the integral. Restricted to the part at 0 is the principal symbol. Yes.
If you fix the resolution at 1, U and F are not like unique, but how many choices do you have? It's unique up to some.
Smoothing.
The resolution at 0, it depends only on the resolution at 1?
Yes, once you take integral from 0 to infinity. Yes.
The extension is only defined up to.
Yes, if it vanishes at 1, so for example, if this thing is 0, this thing is 0. That's automatic. Okay. If you take integral from 0 to 1, that's not true. If you take integral from 0 to infinity, it is true. It's the same as the classical principal theorem.
Why do you restrict it to G times 0 and not the family
It is
of
G
quotient
at 0.
sections?
It's really
I
G.
see. Oh.
Yeah, you should write G. Why don't you write G with a 0?
So it's restricted at t equal to 0. Now, I don't really plan to go much further in this direction. I want to talk about the index theorem. So in the next, I will just say more or less quickly what we do from this point on. So first, there is a technical condition which I'm ignoring in the fact that this thing, technically we don't work with all C infinity functions. We restrict to a smaller class of C infinity functions because this integral, so this is the first condition. So for the classical pseudo-differential operators on the tangent groupoid, I needed that this function from R plus a star to C infinity functions of. So before I needed that this admits an extension to R plus for the integral to be well defined. Unfortunately, here it happens that if you start with a C infinity function, any C infinity function, this does not necessarily extend to R plus. Okay? The problem, very easy to explain, is that this action here acts on subspaces, and so it has some dynamical system. There is some dynamical system which comes from the fact that you are applying dilation to. You have a vector space which is graded, and you apply graded dilation, but on the Grassmannian. And so you have to restrict to some special functions for which this thing admits an extension t equal to 0. So that's a technical issue. That's not very problematic. You also define theta 1 of x1, theta 1 of xn. So these were the vector fields which satisfy Hellman's condition, which we started with. You define these in C minus infinity of G, omega half, R and S. So the way you define them is using the quotient map. These things are vector fields. They are elements. You have x. You start with these elements, which are elements in the Lie algebra. Then you view these elements as left invariant vector fields on the group, and then you let them act by the usual way on the group, and then you descend by the quotient map. And so you can, and this theta 1 of xi star f. On the non-zero part, it's just t xi f on the x of x, y, and t. So it's just a vector field acting on f on the x coordinate. So it's the same formula, but it admits an extension. Because of the density of m cross r plus star, if this exists, it's unique. So you just need to show that it exists, and the extension exists. And to show this, you just go to the quotient map, you do it above, and then you descend. Okay? But everything comes from the fact that these vector fields live on the group. Once you know how to do this, you know how to define theta k of a differential operator by writing it as a polynomial in the vector fields. And so you can define C infinity functions which vanish up to order k. And so you can define higher order pseudo differential operators. And you also get the fact that the principal symbol of differential operators is well defined for free, because it will be just the restriction of what happens at t equal to 0. So already at this point you proved that the principal symbol is well defined. Okay? The only part which I did not mention, and I will not mention, which I'll not do in details, is the fact that if the principal symbol vanishes, then the operator happens to be compact. This comes from the fact that this thing is a C star. You can complete, so the only part which is now not trivial is that if sigma of p, x, and pi is equal to 0 for all x and m, p is a pseudo differential operator of order 0. And pi is into x, this is one trivial representation removed. Then p from L2 to L2, this is compact. And here you need to use C star algebras. So you need to take C infinity function with compact support, and you need to complete this to a C star algebra. Once you complete this to a C star algebra, so the key point that you need is the following. You have a function here. Okay? So on the non-zero part, it's just a function on m cross r plus star. So for every t in r plus star, you can restrict your function to m cross t, and so it becomes a smooth function of m cross m, so it's a regularizing operator. So you can study its L2 norm. Its operator L2 norm, so bounded operator on L2 of m. And the key why we look at this. If you look at this integral, if I didn't integrate from 0 to 1, and I just integrated from 1 to something epsilon is positive, then the integral is already a C infinity function with compact support. So the pseudo differential part of this integral only comes from what happens at 0. And so if I want to estimate this modulo compact operators, then in reality I don't care about the integral from 0 to 1, I just care about the integral from 0 to epsilon, for any epsilon. So if I want to study these types of integrals, their norms, modulo compact operators, I'm really studying this as t goes to 0. And so I need to understand how this goes as t goes to 0. And here is where C star algebras come into play, because what you show is that, so it doesn't necessarily converge, but its limit supremum, which is good enough, converges. So the limit supremum as t goes to 0, this you can write it as the supremum. So when t goes to 0, your function becomes localized at what happens on your group width at 0. And so and so this will only depend on what happens at t equal to 0. So this would be supremum at x in m, pi into x, pi of f at t equal to 0. norm of this. Or I could also write it as supremum of x in M, H in Gx0, norm of so at t equal to 0. Now here it gets a little bit problematic.
If t equals to 0, look at its sister norm.
Yes. Yes. Which, because my group it disintegrates at t equal to 0 to disjoint union, my sister norm becomes just supremum. So I get this type of inequality. Now the advantage of this inequality is that now if this thing vanishes, if f at t equal to 0 vanishes, which is not exactly the same as this condition, this would be that the integral vanishes, but if this thing vanishes, then I know that the limit supremum vanishes, and I can translate this to the statement that the integral gives me a compact operator. Okay? So that's more or less how you go from C differential operators, how you prove this statement. Okay? Now in the last 20 minutes I can do index theory. If I want to be very precise, because I don't really like writing incorrect equations in a recorded video, technically here this equation, this is not well defined for any smooth function. It's only well defined for these special functions for which alpha 0 is well defined. Okay? Technically, I will not use the whole C-star algebra, but I will use a sub-C-star algebra. Anyway. So now I can do index theory. So, much simpler. So if I have a linear map between two vector spaces, so I changed topic, go to something much more fun. So if I have a linear map between vector spaces, then I say that T has finite analytic index if the kernel of T, if the dimension of the kernel of D is finite and the codimension of the image of T is finite. Okay? Now we can take this theorem. So this follows from our main theorem, which is this resolution of this alpha-Noriga conjecture. So if D, so now if M is a compact manifold, D differential operator of Hollander order K such that for every x in M and for every pi in tau x except the trivial representation, sigma of dx and pi. So this was a linear map from C infinity vectors to C infinity vectors. Before, for maximal hypoellipticity, I only needed this to be injective to get maximal hypoellipticity. And one formulation was that this is equivalent to being left invertible modulo compact operators. To do index theory, this would give me just that this is finite. To do index theory, I also want this to be finite. And so I will suppose that this is bijective. Then I will write multiple linear maps. All of them has finite analytic index. And so I didn't write it, and then in this case you define the analytic index of T as dimension of the kernel of T minus codimension of the image. And so here then this map, if I look at it as a map from C infinity functions, or if I look at it as a map from C minus infinity functions, so distributions, or if I look at it as a map from Sobolev spaces, here S is any element in R. All of these have finite analytic index, and the analytic index is the same. Have finite analytic index. It's a theorem, but it's really just a proposition. It's just that the kernel of your differential operator consists of smooth functions. Okay. For the codimension, it's because you just look at the dual, and the dual will also be maximally hypoelliptic because I supposed it to be bijective. So it's not really just a theorem; it's more of remark. It's the analytic index. It doesn't matter how I look at it. I'm just computing the analytic index of this linear map. Doesn't matter which one. So now, just like in ATS Singer, I want to write this analytic index, but in terms of this family of linear maps. So in what follows, I will describe the topological map which gives you the analytic index. So the first part, okay, so if you remember from ATS Singer, the first step in ATS Singer is that they define a class of the classical principal symbol in the K-theory of T star M. So in my case, I need to find the analog of this T star M. And it's not hard to guess. I just need to put all of these representations together. So it's actually quite simple. I start with this T star algebra. So this is always the group, the group integrating the Lie algebra. Tensor, continuous function on M. And here I'm supposing that M is compact. So it's just continuous functions. There's no C0. So this is a C star algebra. And if you call this C star algebra and its space, the space of irreducible unitary representation, of this C-star algebra is the unitary representation of G cross M. They're quite simple. You just evaluate at a point in M, and you take an irreducible unitary representation of your group. So this thing is very simple. Now, I would have used this space if here I had all irreducible unitary representations of the group. I don't. So I need to reduce this C-star algebra. Instead of looking at all reducible representations, just look at a subset. So in G hat cross M, I have this set. So this is a set of representations. This is closed. This is always the same thing because these things are obtained as closure of something. Okay, so it's closed with respect to the Feld topology for this. Now, from general theory of C-star algebras, that's the same as in algebraic geometry. Closed subsets of the spectrum are quotients, are ideals, quotients. So you have a closed set. This corresponds to a quotient. So you can define a quotient. I would call it C star T, to the quotient of C star G tensor C of M corresponding to this. Okay. The quotient corresponding to this means that whenever you have an element which is in the kernel of all of these representations, you take the ideal which is the intersection of all of the kernels of these representations and you quotient by this ideal. Each element here is a representation. Take its kernel, that's an ideal. You take the intersection of all of these ideals, that's still an ideal, and you quotient by this ideal. So you get a C-star algebra. I call it C-star Tout because it combines all of these representations together.
This is the image of C-star G tensor Cn in the groupoid theorem.
Almost. It's the functions which I did not talk about.
So, but it is, so you have this image.
Yes.
It is really this image.
So this is essentially what happens. This is essentially the C-star algebra of the groupoid at t equal to 0. Yes.
It's a subalgebra.
Subalgebra. So C-star 2 would be a subalgebra of, you take the C-star algebra of the groupoids that I just defined, you restrict it at t equal to 0, and that's a sub-C-star algebra. And that's how we prove the index theorem. So. And the way it's constructed makes it so that the irreducible unitary representations of this are this set. So before I had all of the representations of the group, now I restrict it to a smaller C-star algebra whose irreducible unitary representations are precisely the ones I want, nothing more. Now, I can erase this. Now, before I erase this, so for every element here in M, and for every representation except the trivial representation, I have a map here, which is bijective. Okay? Let me just remark that C star Tout in the classical case is just T star M. In the elliptic case, it's C0 of T star M. In the elliptic case, Tout X is just the dual of T star of the cotangent space at X. And so this thing is just the cotangent bundle. And so the space whose irreducible representation of the cotangent bundle is just this. So this is in the elliptic case. So in the exact same way that Atiyah and Singer in the classical case glue together the classical principal symbol to define an element in the case theory here, this invertibility condition at non-zero representation, you can put all of them together to define a class in the case theory, 0 below because it's now C-star algebras, of this C-star algebra. Now, what I need is to start with this element and get an integer, which would be the analytic index. Just like Atiyah and Singer do by taking the Chern class and then integrating against characteristic classes. So we'll do this. So now I can erase this part. So the first thing you notice is that this C-star algebra is not commutative. Because in general, here it's commutative for the classical case, but in general it's not commutative because it involves my free nilpotent group, which is not commutative. So the first step is to replace this C-star algebra with a non-commutative space. So it happens that if you look at this space, which is this, so this space, if you look at it inside G star cross M, here I use orbit method. It's a set of representations, so by the orbit method, it's a subset of G star. So I really look at each representation, I look at it as the whole orbit. Okay? And so it gives me a subset, which is locally closed, so this is a locally compact. So Tout is given by the subspace topology is locally compact, and of course Hausdorff space because it's subspace. So what I want to say, it's a locally closed subset of this, and so I have this. Since it's a locally closed subset, it's a closed subset, not locally closed. Yeah, it's a closed subset, so it's locally compact. So I can define continuous functions, which vanish at infinity, of this space. So this would be the commutative version of this thing. It would be equal to this if my group was commutative. But my group happens to be non-commutative, so I have this. And so theorem, both of them have the same case theory. They don't have the same, they are not the same C-star algebra, but so we prove that case theory of this, there is an isomorphism, I would call it quantum. So it's quantum, which goes from this to this. So this is the same thing as the case theory of C0 of T. That's by definition. So it's the topological case theory of the topological space too. So we had a non-commutative C-star algebra. Using this map, we changed it to a commutative, to the commutative version. Essentially, the group is not commutative, but at the level of case theory, I don't care. Here, I use crucially the fact that the group is nilpotent. Okay, this is a variation of an Tom isomorphism, which Kohn proved. Okay. Now, I'm almost there. So I started with an element which lives here.
This is contemplative equivalence. So you have an action.
No, it's slightly, the proof is more subtle. You can ask the question if I finish in 5 minutes. I don't believe I will finish in 5 minutes, so you will probably not ask your question. But if I do, you can ask it. So I started with an element here, and its image lives here. Okay? Now, here is a small trick. So how did I obtain this space? Okay, so I obtained it, if you remember from my second course, I obtained it as limits from cotangent vectors. There were multiple points of view to this Helfer-Noriga set. One of them was that an element in G star exists in tau x if I could find the sequence xn which goes to x, xin in the cotangent space. So xn goes to x, xin in the cotangent space, and tn which goes to 0 such that xin circle alpha tn, this thing would converge to xi. Okay? And here I had natural xn star of this. Okay? This is a non-Grassmannian version of the Helfer-Noriga. So this is the original description that Helfer-Noriga used in their conjecture. And so remember that before, when we constructed our Gopo AG, we had the space of the tangent vectors. They were also obtained by something like this, and we transferred this formula to a topological space, which was G0. We'll do the exact same trick, but to now this point of view of the Helfer-Noriga set. So this way you get a set, which is, so this way you can construct a topological space, I will call it Z, which is T star M cross. So the one from before, the one that I used, so I don't need this. So the one from before, the one that I had, was M cross R plus star union some set 0. And these were subspaces of my Lie algebra. So this was the Grassmannian version. Now I need the cotangent vector version, which would be the exact same, but now I transfer this into the way to define topology. So this becomes the exact same trick. I have an inclusion. The way I defined it is by defining an inclusion of this inside a space and take the closure. To define this the exact same way, I have an obvious inclusion from this inside G star cross, so I replace the Grassmannian with G star, cross T star M, which cross R plus, which takes xi, x, and t, gives me, so here it's again xi, x, and t, just like from before, and it just takes this. It's the orbit method point of view instead of the point of view as induced representations. So this space is now locally compact because it's constructed as the closure of some space here. So it's a closed subset of this. So it is locally compact. So we constructed a space here, which is a cone. Its base is tau, and it's a cylinder on T star M. But when you have a cylinder, you have an excision from algebraic topology. And so excision tells you that you automatically, because this space exists, you have a map from K0 of the base, which is tau, to K series of the fiber, which is T star M. So I started with my symbol, which lives here, used quantum to transfer it to an element here, and used the excision, because I also need to remember how my representations came from the manifold, to go here. And now I end with the map that Atiyah Singer used, which is the topological index formula, or the analytic if you want, doesn't matter. So the index that Atiyah Singer defined to Z. Now our theorem is that when you do all of this, you end up with the analytic index. So theorem, under the same hypothesis from before, if for every x in M, pi in tau x, except the trivial representation, this thing is bijective, then the analytic index of D, and here it doesn't matter, as I said from the theorem from before, you either look at the infinity functions or distributions or sublog spaces, they all give you the same thing, would be the same as the composition of these three maps. The topological index of the excision of the quantum of the principal symbol. I will end by saying that it doesn't look like this is actually computable. I mean, from an outsider point of view, it looks like you didn't really solve anything. The right-hand side is not particularly easier to compute than the left-hand side, but the right-hand side, you can compute it. It's not particularly complicated because essentially because you understand very well the representation theory of the nilpotently groups. You have the orbit method, so you just go through the representations. The computation gets complicated when there are multiple types of representations which appear, especially those which are infinite dimensional. If the manifold itself has a topology which is complicated. But for simple manifolds, say the torus, things like this, and for situations where the Hörmann's vector fields are not very complicated, say something like this. So, because in this case, the set tau x is particularly nice. Okay, you can actually do computations quite easily. And so, using this, you can give concrete new computations of analytic index. I stop here.
The space-time is, in fact, the closure of, if you take the foliation.
Yes, yes. It's the closure of T star M cross R plus star in the dual space of your foliation on the cotangent space of the singular foliation that you define with underlined x. Yes. And that's not a theorem, it's basically definition.
So if the G is, say, the Heisenberg algebra, where the orbits are really very simple, what would be the set tau?
So it's not the group which determines, it's the vector field. And because you see that tau comes from the manifold.
Yes.
Yes. So, for example, in this case, which is, and tau is local, so the tau is local, so I could just, when I do computations using tau, I could just suppose my manifold is Rn. Yeah. So in this case, if your vector fields are d over dx and x bar k dy, tau at the origin. So it's the only point. When x is non-zero, it's only characters, so you don't care. At the origin, you have two types of representations, just like the Heisenberg group. You get the characters, which are parameterized by two variables, and these are the ones. So I will describe the differential. So these are the ones which take the first one, gives you ixi, and the second one gives you I eta and 0 for everything else, because it's a character. And the second ones, they are also parameterized by r plus star, like the Heisenberg. I'll just describe the plus or minus. And so in this case, it's a representation of your group, which acts on L2 of R. And in this case, d pi, it's just this, but as if it was harmonic oscillator. So you would act d over dx would be d over dt. Say t is a variable in R. And the other one would be plus or minus the representation I t power k. So if k is 1, that would be the Heisenberg representation. Here, what's interesting is that the group is not at all the Heisenberg group, and so it has many more representations. But for some reason, when you compute these orbits, you find out that the only representations in tau of x are these representations. You can prove a general theorem, which is what do I want to say? So this is acts on L2 of R. Okay. When you act using the orbit method, you act on L2 of some Rk. K is some space, Euclidean space. You can prove a general theorem that if you act using the orbit method, you will never go higher than 2 times the dimension of the manifold, or something like this. I forgot the exact estimate, but I have it in my paper. And so the point is that here, because you have a torus, it's not surprising that the very high dimensional representations of this group don't appear. You cannot create representations that are much more complicated than your manifold. Let's put it this way. So there is this, at least, nice thing about it.
All representations of dimension 2 things
here?
H.
Yes. So yes, it's what I
just some representation of these ones, so they have to be finite.
And G over H has dimensions the manifold. So it comes from this. It's a very easy statement, but I really like it. Anyway, so since here you have, for example, 2 just representations, computations of the index in these examples is very easy, because you just do mere vectors on these 2 things. And the only hard part is just keeping track of the signs, because here there are signs and here there are signs of orientations and so on.